In the previous episode of this two-part mini-series, we talked about some of the evidence for the origin of snakes and the issue of which group of lizards they evolved from. Now we're going to talk about their continued evolution within the clade of snakes, remembering that there are currently around 30 taxonomic families comprising 520 genera and nearly 4,000 species of snakes that are still alive today. No telling how many more there were in the distant past, but their fossils show that they were already spread all over the world 100 million years ago. So there was a lot of them, and they were quite a successful group. There is a debate over whether snakiness evolved for swimming, like eels do, or for burrowing, like worms do. Because early snakes were so closely associated with aquatic dolichosaurs and marine mosasaurs, it was thought that snakes lost their legs in the water and then moved back onto the land. But the fossil record isn't really clear on that. There have been some snakes that appear to be in either camp. Of the two-legged snakes, Pachyrhicus and Hasiophysis were interpreted as sea snakes, and Eupodophus was definitely a sea snake, even having a flattened tail for swimming. But the oldest of the known two-legged snakes, Najash, is known from a lake deposit, so it wasn't marine and was therefore more likely terrestrial. The earliest snakes ever discovered are of similarly uncertain adaptation, and they appeared some 50 million years before mosasaurs returned to the sea. So while there is a distant genetic link between snakes and pyramids, there's not necessarily an ecological link. Although the two earliest snakes ever discovered are known only from some skulls and vertebrae, researchers say that it is likely that they had 4 legs, since they lived tens of millions of years earlier than those that still had 2 legs. Also, I have to wonder, if snakes were lizards that took to the water, then why didn't they do like every other lepidosauromorph did when they went back to the sea? Ichthyosaurs, plesiosaurs, and mosasaurs all kept their feet, albeit as flippers. No. It seems to me that snakes did what so many other lepidosaurs did when they went underground. They lost their legs burrowing under significantly greater selective pressure to streamline for the confines of tunnels. This would also explain their fused eyelids and closed ear holes, to avoid scratched corneas and dirt in the ears. But if there is still any question about that, then let's look at their taxonomy. Phylogenies are primarily based on genetics, DNA, which we usually only get with living animals. The clade of modern snakes is in the taxonomic suborder Serpentes. That covers all the snakes there are. But if we're going to include ancient, primitive fossil snakes too, even the ones that still had legs way back then the categorization for all snakes that ever were is Ophidia. And looking at modern snakes, the living ones for which we have DNA, our current taxonomy has one group, Ophidia, as the most primitive of all living snakes. As you might expect of the oldest surviving group, they have a family with global distribution. But it's not just that one family. There's another smaller family only on Madagascar, another family specific to Southeast Asia, and another family in the Americas. Collectively, this entire group is known as the blind snakes. They have eyes, albeit very small ones, and they are almost all blind because they are burrowers. Anomalopetidae is an outgroup family that are also burrowers, and they look like blind snakes, but they're a bit more like boas, which are our next most primitive living snakes. Yes, there are features about blind snakes that are primitive, but at the same time they're still alive, so they're still evolving, and they are quite derived to be blind. They're a really old group too. The earliest one found so far is Boipiba taiensuensis, dating back to 88 million years ago, except that one was 3 meters or 10 feet long, looking more like a boa constrictor. And at that size, it may have lived more like a boa, meaning that while there was already a distinct clade for today's so-called blind snakes, back then they probably weren't blind yet. Intermediate between these blind snakes and a more boa-like form is the fossil Dinalicia, a relatively large ambush predator from the late Cretaceous, being 2 or 3 meters or 6 to 10 feet long. The skull morphology is similar to Boids, suggesting that it was able to take down large prey like modern boa constrictors do, except that this one lived in a more desert-like environment. It is possible that snakes began as swimmers, that they became fully aquatic and lost their legs, and that all the snakes we have today are from a genetic bottleneck, from one surviving group that happened to readapt to living on land again, and then living under the land as well. But there's not much evidence of that, and it doesn't seem likely. Not if these fat-bodied, fully terrestrial families were already around 90 million years ago, and this one is morphologically so close to the crown of all snakes. Deinonychia patagonica shared traits with modern burrowing squamates, specifically a unique spherical vestibule in the inner ear as compared with swimming snakes. And again, this indicates a terrestrial, semifossorial burrowing origin. Another Cretaceous snake, Coniophis, lacked vital adaptations required for marine life. Instead, it had several anatomical features that supported a burrowing nature. Paleontologist Michael Caldwell said that fossil snakes such as Deinonychia are similar to the oldest known snakes, while Coniophis was more similar to a Madstoid snake. Now, we can't talk about the evolution of snakes without mentioning Madstoidae, which is an intermediate group between the more ancient form of primal serpents and the more advanced modern snakes. The oldest Madstoid on our list was Sanage from the late Cretaceous in India. And one fossil shows a moment frozen in time, and probably by a sudden mudslide, wherein a 3.5 meter long, 11-foot snake was in a clutch of dinosaur eggs trying to eat a newly hatched sauropod that was less than 20 inches long. The name Sanage means ancient gape, referring to the fact that Madstoid jaws weren't as flexible as those of modern snakes, imposing a tighter limitation on how much their mouths could engulf. Our next Madstoid is Gigantophis, from 37 to 35 million years ago, in what is now Algeria. And you can tell by the name. Ophis means snake, and the descriptor giganto is like the scientific term for big-ass snake. These things were 9 to 11 meters, or 30 or to as much as 35 feet long. And that is longer than even the longest world record python ever. As Madstoid snakes died out on other continents, they survived until the Oligocene in South America and India, and into the Miocene in Australia. Urlunger lived there from 23 million to 11 million years ago. At 4.5 to 6 meters, or 15 to 20 feet long, it was Australia's biggest snake until it was replaced by the scrub python. The Wanumbi was almost as big, up to 6 meters or 20 feet long, and they held out in Australia until roughly 40,000 years ago. And they apparently interacted with the Aboriginal people. These last Madstoids may even have eaten a few of the local children. Ancient rock paintings reportedly depict Wanumbi as the rainbow serpent of the Dreamtime. Looking back at serpentine taxonomy, if we were to include the extinct Deinonychia with the extant forms, they would be classed as either a basal or sister group of all living Henophidia, which is all living snakes except for the so-called blind snakes. Deinonychia, then, would be less like the American blind snake and more like the Mexican thunder snakes. Up to now, serpentine evolution has been all about whatever features they lost from their lizard ancestors. Legs, eyelids, parietal eyes, external ears, and they still have more to lose. But from here on, we'll also be talking about new adaptations to compensate for those many shortcomings. And first among those new evolutionary developments is this. Just as Madstoid snakes are known for the old gape of not being able to open their mouths any wider than monitor lizards could, we're now getting into Macrostomata, from the Greek for big mouth. This is where the jaw has separated into two bones held together by elastic tissue such that they can move independently. Then the quadrate bone, that we don't have, also flexes on an already flexible skull, allowing their mouths to open so wide they could even swallow themselves. On this branch we have the heavy-bodied constrictors, the boas and pythons, in addition to cylinder snakes, pipe snakes, and shield-tailed snakes with pointed heads and hardened shields on their tails, such as no other snakes have. Up to now, primitive snakes have either belonged to the clade of blind snakes or they've been said to be like boas. And now we're finally at real boas. Two things about that. First, remember that Madstoid snakes were once all over the world. And then when they died out everywhere else, they dominated the island continent of Australia as a final holdout. So too were boids once all over the world. For example, there are 4 fossil boas and a python too, known from the Messel Pit in Germany, a country not normally known for giant constrictor snakes. But there are no European pythons anymore, and boas are all but extinct everywhere else except where they dominate in their last holdout, which was the island continent of South America, until it joined with North America. The biggest boid species today is the anaconda. It's the modern world's heaviest and second longest snake after the reticulated python. The biggest snake ever in geologic history was also a boid, essentially a giant anaconda, a giant among giants. Titanoboa was the apex predator of the Paleocene, up to 15 meters or 50 feet long. It was at least 13 meters or 42 feet long and 1 meter or 3 feet wide, and it was estimated to have weighed 1,100 kilograms or 2,500 pounds. That's a hell of a snake. What was once just the stuff of fantasy novels and cheesy action movies is now in reality the biggest snake ever known to science. You might think that what we call boas is a consistent clade and the anacondas are something else, but that's not entirely accurate. The red-tailed boa constrictor and rainbow boas are actually different sets. Turns out rainbow boas were misnamed. They are a clade unto themselves, since all of them are more closely related to each other than any of them are to anacondas, but some anacondas are more closely related to rainbow boas than they are to other anacondas. And that means that the rainbow boa are a genetic subset, a daughter clade of miniature anacondas. Now, the same stock that begot boas also separately produced pythons. Boas and pythons are both heavy-bodied constrictors, but they are actually different clades. Molecular clock analysis of their DNA shows that boas and pythons diverged from their last common ancestor roughly 70 million years ago, back when they were still dinosaurs. And we should note that the closest living relatives of these type snakes are small burrowers that don't look much like boas or pythons. So their evolution is convergent. They're just big, fat, primitive snakes that happen to look like big, fat, primitive snakes. Although pythons are a bit more advanced. Most pythons, for example, have heat-sensing pits in their faces, one of those evolutionary developments I mentioned earlier. Boas give birth live, while pythons lay eggs, and pythons have more bones in their skulls and more teeth as well, sometimes even additional rows of teeth. Frighteningly long, recurved teeth, too. So why did I say that they're both primitive? 2 reasons. First, remember when we left off in the previous episode, I mentioned that there are now 4 fossils of true snakes, known from 100 million to 92 million years ago, with no evidence of forelimbs or shoulder girdle, but they did have these pathetically puny vestigial back legs. And 3 of these 2-legged snakes were found in the Middle East, but the 4th one was in South America. That one, Najash, didn't just have back legs. It also had a sacrum, the vestigial remnant of a pelvis. It also still had a pelvic girdle, both of which are absent in modern snakes and in all other known fossil snakes as well. In fact, some serpent lineages, like Shelphus, for example, had already lost their back legs when these others still had them, and these different groups of 2-legged snakes must have retained those legs for quite a long time in order to distribute that trait onto both sides of the world. We know it was at least several million years, and probably a lot longer. So why did they lose their front legs so easily, but keep the back legs for so long? A likely answer to that may be found in the modern yet primitive constrictors, the boids and pythons, and basal uniliids as well. All of them have a vestigial pelvis in the form of cloacal spurs, the last remnants of those back legs, which they use to embrace and stroke their partner, because these snakes find spurs to be stimulating sexually. If such appendages were ever necessary for snakes to mate, they're not anymore. And that, I think, is why they held onto their back legs for so long. But those legs still shriveled into these tiny spurs, and then, in more advanced derivations, even the spurs eventually disappeared altogether. The other reason that these snakes are so primitive is another ancestral lizard trait they retain. Boids, pythonids, and some Europeltids still have 2 functional lungs, though they are asymmetrical. On all of them, the left lung is smaller. A boa's left lung is only 3/4 the size of its right lung, and the left lung of Europeltids is either very small or absent altogether. In most snakes, and in all the more advanced ones that we'll talk about in a moment, the short left bronchus terminates into a rudimentary vestige of a left lung, which can be used for buoyancy for swimming, but it's otherwise useless. They have only one elongated lung that can be used for breathing. Understand that each of these links is not an individual species. They're at least a genus, and most of them are taxonomic families. For example, Boidae is a family consisting of 5 subfamilies, themselves comprised of 12 genera and 49 species. Pythonidae is another family made up of 10 genera consisting of at least 42 species. But many of these links are even bigger categories than that. For example, this next one, Henophidia, is a single parent category inclusive of all these other clades to follow. Acrocordidae is an interesting one to start with. These are water snakes, and with species names like the dogface snake and wart snake, we'd be right in guessing that they're not pretty. Today, this group is known for hideous things like the elephant trunk snake. They're heavy-bodied too, but they look like they've lost a lot of weight because their skin is too big. They live their whole lives in shallow water because they can barely move on land. However, way back in the Eocene, 56 to 34 million years ago, this group included sea snakes, and one of them was the biggest sea snake ever. Paleophis colosseus was 8 to 12 meters, or 30 to 40 feet long, a literal sea serpent living up to the imaginations of the ancient mariners. This gets us to colubroids, the taxonomic subfamily of the so-called advanced snakes. They're typically leaner than most modern serpents we've yet seen. They've lost not only their left lung, but every species in this clade is also living without their left carotid artery, the vessel that brings blood to your brain and face. I guess snake heads only need half as much blood. Looking at this chart, it seems as if we're almost done. But the few remaining links in this one superfamily represent at least 80% of the snakes that are still alive anywhere. That's well more than 3,000 species. So we could say that we're just getting started, but there isn't time for all that. So we're just going to look at some of them, and I'm going to skip over a few of these because we're going to come back to them in a moment. Let's jump right to Colubridae, the largest single family of snakes, with some 250 to 300 genera and around 1,800 to 1,900 species. That's rat snakes, corn snakes, king snakes, milk snakes, pine snakes, beauty snakes, indigos and crebos, and a whole lot more. This clade used to be even bigger than it is now because it was once a sort of taxonomic junk drawer wherein they would put all the colubroids that weren't obviously something else, like cobras or vipers.
How should we classify dragon snakes with those raised rows of ridges down their backs? Into what clade do we put tentacle snakes that evolved its own unique sensory appendages on its face? Where do we put Iwasaki's snail-eating snake that has an asymmetric mouth with fewer teeth on one side than the other to better accommodate eating snails whose shells are always spiraled the same way?
I don't know. Do they all have just one lung and one carotid artery?
Yes.
Well, then they're all colubroids. Do any of them have fangs? In the front? Then they're neither vipers nor lapids. Put them in the everything else category. Colubridae.
That's how it used to be, back before we could access the genome to know where they go. Colubridae is not a junk drawer anymore because geneticists have done molecular phylogenies and all of these things, and they've removed a few groups that didn't really belong there, like Xenodermidae, where the dragon snakes go, Periidae, where the snail-eating snakes are, and Homolopsidae, where the tentacle snake really belongs. Now genetic data implies that everything that remains in Colubridae really is supposed to be there. They've been more or less genetically vetted, such that Colubridae is now a proper monophyletic taxon. However, if you look at all the surrounding colubroids and compare them collectively, you'll note that the common ancestor of all of them must have been something that, decades ago, would have been carelessly classified as a colubrid, being a sort of template for this entire assembly, meaning that it's the basal form of a relatively lean, advanced, and, until now, non-venomous snake. But that's about to change. While colubrids are mostly harmless, even some of the cute ones that children might keep as pets, like these beautifully colorful garter snakes with no fangs at all, may be mildly venomous, though they're still safe to keep and harmless to handle. Snake venom is made from salivary glands that may produce additional proteins, and these proteins can vary and do vary from species to species and over many generations, where natural selection is, in a sense, blindly and unintentionally experimenting with which toxic concoctions produce the best results over time. Thus, an impressive variety of types and mixtures and concentrations of surprisingly complex cocktails have been derived in different lineages. Some venom only helps the snake to digest, but that might also cause necrosis in a bitten victim if they get away. Another venom type attacks the victim's nervous system, causing convulsive seizures, so that if it does get away, it won't get far. Other types of venom change the blood pressure or destroy the blood clotting ability, in either case potentially causing heart failure, and in every case making the prey safer to subdue and so easy to do that most snakes can disable their prey without even using their hands. If any species happens upon some type of venom that works for them, there is usually a selective pressure to keep it, though not always. And once they have it, natural selection will likely also improve upon it, though again, not always. The major toxins of the most medically important taxa of venomous snakes were determined by first-generation approaches including protein chemistry, comparative pharmacology, and cladistics methods borrowed from evolutionary biology. Now the debate is over the validity of Toxicophora, the parent clade of anguimorphs, iguanids, and Ophidia, also known as serpentes. Did the propensity for venom originate 200 million years ago with the common ancestor of snakes and all venomous lizards collectively? Between anguimorphs like monitors with hemotoxins and Gila monsters with neurotoxins, as well as bearded dragons and other iguanids now being classified as mildly venomous but with a different type of venom? If that trait evolved from a common ancestor of serpentes and other venomous lizards, then why are the venom glands in the top jaws on snakes and in the bottom jaws on anguimorphs? If venom evolved only once in the distant past, then why did it take 100 million years to finally exhibit this latent ability? And then just in this one subset? Or did the propensity for snake venom evolve independently, separate from lizards, arising in snakes only in the specific category of colubroids? Some venom can be quite potent chemically, yet still be ineffective if the means of delivery is so inefficient that not much of it gets into the wound. So a species that has venom would do well to grow the right sort of teeth to inject it. The colubrid family generally have much smaller teeth than pythons and boas do, or they may have no teeth at all, like in the case of the African egg-eating snake. They stretch their toothless mouths over the whole egg, which is then punctured by structures in their spinal vertebrae that protrude into their throat. This also allows them to regurgitate the entire eggshell all in one piece. And the point is here that teeth can evolve to be longer or shorter, but some colubrids have a mix of both long and short, where the front teeth will be as small as lizards' teeth, but the back teeth at the rear of either side of the top jaw can be just as long and curved backwards as they are on pythons. Snakes with extra long recurved python teeth in the back of their mouths are said to be rear-fanged, and there are several colubrids with this configuration. In fact, the majority of all venomous snakes in the world are like this, and some of them have grooves along their fangs to better enable that venom to drip down and into the bite. One example of this is the hognose snake, which is a popular pet despite it looking like a psychedelic slug and being rear-fanged and technically venomous. Some people still think they're cute for whatever reason. Their bite is considered harmless, about as bad as a bee sting. It just depends on how you react to it. Allergic reactions could make a hognose bite reportedly comparable to the bite of a copperhead, so your mileage may vary. And many venomous snakes are like that. But the toxicity of their venom varies with the species too. Getting bit by a mangrove snake might not be a big deal, but getting a bite from a boomslang would be. Because the bite of a hognose is always an unreliable means of self-defense, they usually prefer to play dead. And no one's afraid of a dead snake, but you wouldn't want to eat one either. However, the eastern hognose has another defense mechanism. Many colubrids can flare out their ribs. The paradise snake can do this all the way down the length of their bodies, allowing them to glide from tree to tree. But most colubroids that can flare their ribs only do so along their neck. If you're looking into the face of a snake flaring up like this, they seem bigger than they are, and that is sufficient to deter some predators. And there's another rear-fanged colubrid with the same talent, the South American false-water cobra, which is obviously closely related to the eastern hognose. Both genera, Hydrodynastes and Heterodonta, belong in the same colubrid subfamily, Dipsidae. And you might think that the false-water cobra is trying to mimic an actual cobra, as if Brazilian predators know better than to mess with a cobra. They don't know what a cobra is. New World predators have never seen a cobra. Now, if you hop over to the Old World, say Egypt, for example, they have a false cobra too, a different one that's not a colubrid. And they have real cobras as well, so mimicking a cobra over there makes a lot more sense. And their cobra is also pretty closely related to real cobras. The family Lamphoridae, which includes false cobras, is right next to Elapidae, which includes real cobras, along with deadly sea kraits and tiger snakes, taipans, death adders, mambas, green and black, and other delightful surprises you wouldn't want to find in your drawers. The only elapid we have here in America are 3 species of western coral snake, and they have a few species of eastern coral snake too. Not on the eastern side of the U.S., but on the eastern side of the Atlantic, where they also have their own garter snakes. However, Old World garter snakes are not the harmless western colubrid, but the deadly eastern elapid that you would not let your kids keep as pets. And funny how much both of these African garter snakes look like morphs of coral snakes, which I guess they are, arose by any other name. So colubrids have fangs in the back, if they have fangs at all, while elapids have fangs in the front.
How did that happen?
Well, let's look at the clade between them. Lamprophiidae, a family which includes stiletto snakes and also the Egyptian false cobra. Some of the 89 species in this group have lost their fangs. Others have rear fangs, like the colubroids that came before them, but some of them have their fangs in the front instead. Lamprophiidae is the only snake family with both front and rear fangs represented.
So how did that happen?
The scientists behind this study concluded that the ancestral Lamprophiid was most likely rear-fanged and that the shift in dental morphology was associated with changes in diet. There is also evidence that front fangs arose from a rear-fanged condition, and this has evidently occurred independently more than once within the family.
Okay, but again, how did that happen?
Well, this study looked at the embryological development of front-fanged elapids and rear-fanged colubrids and compared them with fangless boids and a particular Lamprophiid, the African stiletto snake, whose front fangs are mobile, meaning that they can move them around as necessary. So that if you grab one behind the head where you think it's safe, they can still stick one of their fangs out the side of their mouth and jab you with it. These scientists followed the expression of the sonic hedgehog gene in 96 developing embryos representing these four families. And what they found was that in all of the snakes that grew fangs at all, their development always begins at the back of the mouth, the same way on everyone, except the boids, which of course never grew fangs. But then in all the species that have front fangs, something happened, like the mutation, to displace the rear fang, as if it was twisted around to grow in the front instead. But it wasn't just that they were turned around. Expression of fang growth became linked with the development of the venom gland, too, with Lamprophiids developing their fangs in a strikingly similar way to elapids, indicating a commonly derived synapomorphy. But their development was significantly different from the way vipers develop their fangs. Vipers start developing their fangs at the back as well, and they get flipped around too, but in a different way, because vipers are the result of a different but similar developmental change, one that resulted in forward fangs linked with the venom gland, but their fangs are hinged. They can open out and fold back, unlike the fixed fangs that elapids have. This is an aspect of science known as evo-devo, where their evolution is mirrored in their embryological development. They develop differently because vipers evidently diverged earlier than elapids, even earlier than Lamprophiids. That's according to embryology and phylogeny, not paleontology, because so far the fossil record shows elapids in Africa as early as 25 million years ago, whereas the earliest vipers found so far are from within the last 5 million years. And they include a few vertebrae from a Greek viper that might be the biggest ever if we could get an exact measure of how long it was. So the viper's front fangs began their evolutionary and biological development as rear fangs, just like basal colubrids have. And they were repositioned by a different distortion or set of mutations than the other front-fanged serpents. And they all stem from the same template as modern colubrids. Vipers diverged first, then Lamprophiids, and elapids. This answers a question I often hear regarding convergent evolution. Why does the harmless American bull snake do such a convincing job of pretending to be a rattlesnake, going into a striking pose and rattling its tail against leaves or whatever else helps make that noise? They're not trying to be rattlesnakes, and they don't know that they look like rattlesnakes. It's just that tail rattling is already a common threat display among many colubrids. They do that whether they look like rattlers or not. King snakes do it, and they're not trying to look like rattlesnakes. They eat rattlesnakes. And they look more like coral snakes, which isn't intentional either. It's just Batesian mimicry, natural selection working on comparable effects of overlapping populations of different species at once. Even harmless and colorful corn snakes rattle their tails when they get mad. We just don't notice because they're cute. They don't look like rattlers, and we don't usually hear them either because they don't have the annual growth of overlapping keratin buttons on the tips of their tails that make up that noisy rattle. So if we follow the ancestral lineage of all these things, and without even referring to fossils, just using taxonomy, we can see that the last common ancestor of all living snakes must have looked like a cross between blind snakes and boas, and some of them went on to look more like a mix of boas and pythons, while another offshoot lineage lost weight and went on to look like the colubrid collective, some of which grew back fangs. Or they didn't really grow back fangs, did they? The front teeth got shorter, the back teeth stayed long. And then one of those rear-fanged branches became front-fanged vipers, and another line went on to lampriphiids and elapids. And that's how their common ancestral lineage snakes its way through the family tree.
You don't have to like try to rush through it or whatever, but just be like, how do we classify dragon snakes with those raised rows of ridges down their backs?
That's a good question.
Yeah.
Into what clade do we put tentacle snakes?
That evolved its own unique sensory appendages on its face.
Mm.
Where do we put Iwasaki's snail-eating snake? I did it really good. Iwasaki's snail-eating.
I was liking what you were doing. I was hoping
See?
you'd keep doing
Well, yeah,
You wanna
but
go back and
we were
forth?
both reading the same thing. We were reading his line.
it. Yeah.
Okay, hang on.